So good evening, everyone, and a very warm welcome to this alumni webinar series, the first in a series that is the future of physical sciences. My name is James Keeler. I'm the current head of the Yusuf Hamid Department of Chemistry. And it's my pleasure to be your host here this evening and to introduce the three speakers who you'll hear later on. Now, you don't need me to tell you that finding alternative sources of energy is an absolutely crucial thing, which we absolutely must do. But I was at a talk last week, and the speaker came up with the possibly surprising introduction that this problem was already solved, which caused a bit of a rumor around the building. But what he meant, I think, was that we have the mature technologies to capture solar energy and to capture wind energy. And it is, in his view, just a matter of the political will to do this on a large enough scale to substitute for fossil fuels. But there, of course, remains another issue to do with renewable energy, and that is to do with its intermittency. The sun doesn't always shine, the wind doesn't always blow at the right times and in the right places. And of course, we need our sources of energy to be portable as well as renewable. And this, I think, is not a solved problem, and it's a problem which is very much an active area of research here in Cambridge. And our three speakers this evening are going to address this issue about the next generation of energy storage. So each of the three speakers will speak for about 12 or 15 minutes. And at the end of that, we will have time for questions. And if you have questions, you can put them into the Q&A. And at the end, I'll pass them to the various people as we go along. So it's my pleasure, first of all, to introduce Professor Siân Dutton, from the Cavendish Laboratory, Department of Physics, that is. And Siân is going to tell us about beyond lithium-ion batteries. Siân, please.
Hey, all right, let me just, you can't see my presentation. Sorry, hopefully you can see my presentation now.
Almost.
All right, there.
Almost. We're there. Thank you, Siân.
All right, thank you very much, James, for the kind introduction. My name is Siân Dutton, and I'm a professor of physics, and I'm based in Princeton Physics, where I lead the functional energy materials group. So we're interested in exploring materials and understanding how we can control their properties using both composition and structure. And one of the things we work on is how to improve rechargeable batteries, including going beyond lithium-ion batteries. So when we think about battery technologies, we probably think about the batteries we use in our portable electronics and our laptops and our mobile phones. And these have been around for a long time. And they're really, whilst we would obviously like them to be better, to last longer, to have more capacity, they work well. However, we can think about other needs where we might need energy storage, where there are still real improvements or optimization that can be done. So we can think about using batteries to power cars, where we're concerned about range and we need things to be portable. Or we can also think about regulating supply and demand on the grid, where actually we need to be able to store energy at scale, often over relatively long timescales. And then finally, we can think about very small devices for things, sensors and devices within the Internet of Things, where again, we have very different requirements. So I'm going to focus on grid storage. And as James has already mentioned, as we move to renewables, we can no longer rely on regulating the grid by simply burning more gas as demand spikes. So instead, we have to think about how we do this in another way. An example of this is shown here. So this is an example of photovoltaic production. And what you can see in red is that, as one would expect, there's no generation of energy when it's dark. And then there's a large generation of energy peaking at midday when the sun is at its highest, and then this falls off as the sun sets. So this is really, this allows us to generate a lot of energy. However, we then need to think about how we regulate this with consumption, so shown in grey. And we can see that whilst there is some matching, actually, if we want to utilize all this photovoltaic energy that we can generate, we need to find ways of storing it so we can use it at the peak times, including overnight, but obviously we're not going to generate energy. And we have similar things with wind, though that's slightly less predictable as to when one might be generating energy. So as we move to a more renewable grid, and ideally an entirely renewable grid, we have to think about storage. So this is an example on like a couple of hours timescale, but actually the problem we have to think about on a much wider timescale as well. And that's because as we move to electrifying heating and cooling, there are going to be much larger demands, which are going to be much more variable. Over a third of our energy usage is actually on heating and cooling. So there's an example shown here for California. And again, we're looking at energy usage as a function of time of the day. And what we can see here, California is nice and sunny. And so actually the energy usage is maximized in the summer when the air conditioning is on. And it's minimized in the spring when neither air conditioning nor heating is used. And so if we're doing this all with renewables, we need to think about storing over much more extended time periods to be able to accommodate either the increased energy from heating or cooling, depending on where you are on the globe. So what this means is that we're actually going to need large amounts of storage. And so this is a reference case for energy storage from the National Renewable Energy Lab in Colorado in the United States. And what we can see is that there's always been a little bit of storage capacity over the last 15 years, but their predictions of moving from 2024 is where there's a small amount of battery storage in pink and a large amount of mechanical storage in pumped water, is there's going to be significant increase in capacity, storage capacity over the next 25 years. So within this case, 200 gigawatts of storage capacity needed by 2050. And I think just to put this into context, the average UK household usage of energy is 1.2 megawatts. So this is 200,000 household months of energy. So I realize that's not a very useful metric, but it is a large amount of storage that's needed to balance the supply and demand on the grid as we move forward into this sort of new sort of regime of energy generation. So the other thing I'd like to point out is that this is all different sort of degradations of storage. At the moment, we only have battery storage for 2 hours, and this is looking at going forward, extending that storage to much more extended timeframes. And that's important as we go to more renewables, and we need to be able to regulate more effectively. So one way we can store energy is through rechargeable batteries. And this is a way of converting chemical energy into electrical energy. And it's sort of comprised of two sort of solid components, an anode and a cathode, separated by a ionically conducting and electrically insulating electrolyte. So the example shown here is one of the first commercialized lithium-ion batteries, where you have graphite on one side and lithium ions can sit between the graphitic layers. And then you have a transition metal oxide, in this case, lithium cobalt oxide, with lithium sitting between the layers. And when the battery's charged, lithium moves from the lithium cobalt oxide to the graphite, and on discharge, it moves the opposite way. And because the electrolyte is ionically conducting but electrically insulating, electrons are forced through the external circuit, generating the current. And this is how the lithium-ion battery works. So lithium-ion batteries work very well. They're commercialized, they're everywhere. But lithium is actually a finite resource. And as we think about moving to ever expanding amounts of storage, we need to think about alternative ways of doing that. And what I've got on this slide is a representation of the periodic table. I've also shown a more standard convention in the top right. So this is just a way of illustrating the elements. And what's being done here is it's scaled by the natural abundance of the materials. So how much there is available to us to use for different applications. And then there's color coding based on how scarce that is, or how likely there will be limitations on supply going forward. And then actually, helpfully in this one, there's also little phone symbols which show us elements which are used in mobile phones. And this is not just the batteries, but it's also the electronics. So things like copper and silver would be used in the electronics. the touchscreen, indium, yttrium, but also the batteries, which is the lithium and the cobalt. So what we can see here is that lithium is in yellow, and there is a limited availability with a risk to supply. And this means that as we move to having more energy storage, we might want to move away from lithium or have alternatives to lithium for our electrochemical energy storage. And there are lots of different ways of doing this. I'm just going to briefly touch on some work we've been doing on magnesium. So that's here. Magnesium is a divalent ion, so it's got 2+ ions. So what this means is that for every magnesium we move across our cell, 2 electrons go across our circuit. And what this means is that we should be able to generate relatively high capacities compared to for the number of ions moved. Magnesium is attractive, but not only because of that, but also because of its higher abundance compared to lithium, which means that we're less worried about supply. And there being some considerations to do with how magnesium can be incorporated into the battery, which means it's safer. There are some payoffs in terms of the voltage, which can be detrimental, but for some applications, particularly sort of stationary storage, this is perhaps less of an issue. So magnesium-ion batteries were first sort of really reported by Doran Orbach in the 2000s, and there's been a lot of work developing them since, really thinking about how do you take these components from your lithium-ion battery and optimize them for magnesium. And here in Cambridge, we've been looking at this for quite a long time, and we've looked at replacing the graphite. Unfortunately, magnesium 2+ will not go between the graphitic layers. There's too much charge repulsion, so we can replace that with a magnesium bismuth antimony material, which will very readily incorporate magnesium at the voltages sort of equivalent to graphite. We can replace our lithium conducting electrolyte with a magnesium equivalent that allows us to move the magnesiums across the cell. And we can also replace our lithium transition metal oxide with various magnesium containing materials. So the example here has magnesium, manganese, and borate groups, and this can store magnesium in the material. Unfortunately, what we can't do is get all these different components to work together, and so we have to use slightly different cell configurations to be able to do this, and this is one of the challenges with magnesium-ion batteries, which is why, despite being discovered 25 years ago, there's still no real commercially available batteries, though there are some startups which are aiming to do this. So in addition to magnesium, we can think about other elements we can use as our transport agent in our cell. So we can think about other divalent or 2+ cations, so things like calcium, which is larger, so will be heavier, but for stationary storage that may be less of an issue. Or zinc, again, 2+. We could be even more ambitious and think about having 3+ ions, where we're going to move 3 electrons, so things like aluminium. Or we can say, well, actually, lithium 1+ works really well. What about potassium or sodium or potassium, where we can take a lot of the chemistry and replace that? So these are all alternatives which are being explored. Particularly sodium is very close, has some commercialized products, with the others in various stages of development. I'm going to end there. I would just like to briefly thank my group, in particular Camilla, who's done lots of the work in this space, and then to acknowledge that a lot of this work was funded by the EU through the eMagic battery community. And I'm going to hand over to James for the rest of the evening. Stop.
Thank you very much, Siân. That's really set the scene very well, and set the problems and for the future as well. So moving on, our next speaker is Professor Alex Force from the Joseph Mead Department of Chemistry. Now he's going to talk about supercapacitors. Now these might be less familiar to you than batteries, but I think they're around. Perhaps they just aren't so obvious. So I cycled across town this evening to come back to the department, and my bicycle lights stay on after I stop pedaling, even though there's a dynamo, and I think that's a supercapacitor that's charging up there. And I think my car has a supercapacitor in it, which is used for the intermittent stop-start where the engine cuts out when you brake. So they are around, but like all of these things, the crucial thing is to make them really effective. And that's what we're going to hear about from Alex, so whose topic is improving fast charging supercapacitors. Please, Alex.
Thank you very much, James, for the great introduction, and to Siân as well for setting the scene so well. So I'm really excited to do a deep dive review on this topic of supercapacitors and try and give a quick summary of work we've been doing over about the last 10 years in the university, looking at these supercapacitor energy storage devices. So as James said, you've all heard of lithium-ion batteries, and we really like those, but they do have some issues. So you can't charge them quite as fast as you want. So we're all familiar with that. And also they don't last as long as you might like. So after sort of 4 or 5 years, normally your phone battery needs to be replaced. Supercapacitors, on the other hand, can overcome a lot of these limitations. So you can charge these devices up in just about 1 or 2 minutes. So they're really fast to charge up. And they also have a really long lifetime. So they can last for millions of cycles instead of just thousands of cycles in batteries. But the catch is that they don't store as much energy as batteries. So research in this area is generally about trying to improve the energy storage capacity of these supercapacitors. As Siân mentioned, you can use these, and James mentioned as well, you can use these in things like electric vehicles, potentially alongside batteries. And you can also use them for very rapid storage of energy and release of energy on the electricity grid. And this is just an example of an electric bus, which is powered fully by supercapacitors. So what are these devices that I'm talking about? Well, you can make a really simple supercapacitor by putting 2 rods of metal into a beaker of salt water. And so you've got these solid electrodes, which would be our metal, and then you've got a liquid electrolyte. Now, when we apply a voltage across these electrodes to store energy, you build up charge in the 2 electrodes. And at the same time, you're going to bind these oppositely charged ions from the liquid electrolyte on the surface, and thereby store energy. Now, instead of using these simple metal rods, what we instead use are these porous activated carbon electrodes. You might know of these as activated charcoals, which are used in water filters. They're also used in these supercapacitors. And just for a single gram of material that you could hold in your hand very easily, there's thousands of meters squared of surface area internal to the material. So you've got these pores where you can then store your ions and therefore get a large energy storage capacity. So just a word about these activated carbons. Siân talked about the need to work with sustainable materials. And here what we're working with is activated carbons or activated charcoals, and we make them actually from coconut shells. So this is a waste organic material, and you can treat it to get this highly porous and electrically conductive material. Just a word about the structure of these materials. You might be familiar with something known as graphene, or at least graphite. And so graphene is a single layer of a graphite material. So this is what's in your pencil leads, where all of the carbons in the structure, shown by these little balls here, are bonded to 3 other carbons, and you form this kind of hexagonal honeycomb lattice. Now, in these supercapacitors, we're working with materials that have a similar structure, but you can see it's much more messy and complicated. But if you look closely, these activated carbons or activated charcoals, they have these structures which, if you look closely, it looks like little pieces of graphene, but these little pieces curve and bend and stack together to make this overall porous and rather messy structure. And this is sort of where the challenge is in this field. We want to make improved supercapacitors, but these structures we're dealing with are really hard to study and understand. And I'm going to talk about some of the challenges that's thrown up in the last years. But yeah, to be clear, the aim of my study for what I'm showing you tonight is, if we have lots of different activated charcoal materials, how come some of them perform better than others? Why will one store more energy than the other? And therefore, how can we make better supercapacitors? Well, the main thing that people did in the past, and this is over about the last 20 years, is to look at the porosity of the material. I mentioned that these are really porous or sponge-like materials. And what most researchers have done is measured how many pores do you have at different pore sizes? And they then used this data to try and understand the energy storage. And so a study about 20 years ago came out saying that when your pore size of your electrode gets really, really small, and it's of a similar size to the salt in your liquid electrolyte, they found this really big increase in the energy storage capacity. But other studies came along later and looked at a wider family of materials, and they found overall a kind of a lack of trend here. So you can see, as these researchers varied the pore size, in their study, they didn't see the energy storage capacity varying in any kind of obvious way or any systematic way. And so as a researcher, when you see these kinds of contradictory or hard to reconcile results in the literature, that's something to get excited about, because it means there's more going on here than meets the eye. So we've done a study to look at this, which has been led by Xinyu Liu, one of the PhD students in our team. And initially, we looked at the traditional approach. So we measured the pore size of our carbon electrodes for 20 different carbon materials, and we saw how much energy they could store. And again, in our study, we're not seeing any obvious trend here. There's just a scatter of the points across this graph. So at the university, we're lucky to have really fantastic facilities for doing new kinds of experiments. And we thought, let's turn some of our special expertise in new techniques to look at supercapacitors and how they work. And so the technique we're going to be using is called nuclear magnetic resonance spectroscopy. Probably everyone's familiar with magnetic resonance imaging, MRI, where in medicine, patients will go into this large magnet, and then you can use the magnet to get an image inside, for example, someone's head here. In a very similar way, in NMR spectroscopy, we don't measure images, but we use a similar technique to measure a so-called NMR spectrum. And you can think of this as a fingerprint of your molecule or your material. So this is just a quick example to bring you up to speed, but this is ethanol, so an alcohol. And in this case, if we do hydrogen NMR and look at the hydrogen atoms in that molecule, we'll see 3 different peaks in our fingerprint. And it's because there's 3 different kinds of hydrogen atom in the molecule. So we're going to try and turn this technique now to understanding supercapacitors. And so what we do is take our activated carbon electrode, and we're going to soak it with our liquid electrolyte that you'd find in a supercapacitor. And then we're going to take a quick NMR fingerprint again of that combination of the electrode and the electrolyte, and then see if we can use these fingerprints to understand why some electrode materials, some carbons, perform better than others. So just to introduce you to these NMR fingerprints for supercapacitors, these are the kinds of things we see here. So again, it's a carbon electrode material soaked with the liquid electrolyte. And when we've got the carbon and the electrolyte together, what we see is 2 peaks in our fingerprint. Whereas when the carbon's not there, and we've just got our electrolyte, we only see 1 peak. So what's going on here? Well, this left-hand peak is coming from free liquid, sort of sloshing around in between the particles of our electrode. But this right-hand peak, on the other hand, is more interesting. And this is coming from our ions that have gone into our pores of the carbon electrode. And so the ones we'd expect to be involved in energy storage. So what Xinyu did is to measure these fingerprints for a really wide series of carbon materials. And we were really excited in this case to find that these fingerprints, they do correlate with how much energy we can store. So what we look at here is the difference in position of our 2 peaks in the fingerprint, so represented by this delta delta. And what we find when we plot a graph of our delta delta value from these NMR fingerprints is that they correlate really well with how much energy you can store. And this is for sort of 20 different materials from a whole wide range of different sources. And you can see broadly, when we've got a smaller difference between our positions of the peaks here, we get a higher energy storage capacity. So this is where we want to be, in the top right corner. And it sort of tells us where to go. So what's going on here? What does this actually mean if we've got a smaller or a bigger difference in these peak positions in our NMR fingerprints? Well, we were able to analyze that over the past years. And what we found is that basically the carbons that can store a lot of energy are the carbons that have very small fragments of graphene in their structures. Whereas the carbons that can't store so much energy down here, these are actually the ones that are more ordered. So the carbons that look closer to a perfect graphene sheet with lots of these hexagonal rings connected together nicely. So this tells us what we need to do is to make carbons that are more messy or more disordered with these small fragments. And then maybe we can push up higher up here and make better energy storage devices. And just to give you an idea of what these might look like, this would be a model, a molecular model of a very ordered carbon. And you can see the big sheet here of the graphene-like carbon. And so this is one that we would say has a low capacitance or a low capacity to store energy. Whereas these more messy ones with the smaller carbon fragments, these are the ones that our new theory says that you should go after. And so it's a case of what our press team came up with was mess is best. So I don't know if you agree with that or not, but in general, but in these supercapacitors, we find that these messy electrode materials give rise to higher energy storage performance. And so if you're interested to read a bit more about this, you can search for mess is best. And you'll find on our university website, you know, all these great articles about the research that's going on. And this is just to acknowledge Jinyu Liu, who is the lead author, the PhD student in the work, and also my colleague and collaborator, Professor Claire Gray. So just to wrap up, hopefully I've shown you that we can use these really interesting new techniques related to MRI, called these NMR fingerprints. They can help us to understand energy storage. And they've led us in this case to this kind of breakthrough finding that disorder or the sizes of these graphene fragments dictates how much energy you can store in these supercapacitors. Of course, there's always lots more work to be done. We need to understand this better, but we're also now actively working, including together with industry, to then take these insights and make better supercapacitors. With that, I'll pass it back to James, and yeah, thank you very much for listening.
Thank you very much, Alex. Thank you. I have more understanding about how my bike lights work now, I think. Thank you. Okay, so as we move on to the third and final talk, can I encourage you to put any questions you have into the Q&A box, and we'll pick those up at the end. And we'd very much like to pick up a few more questions. So our third and final speaker this evening is Professor Rachel Evans from the Department of Materials Science and Metallurgy. And her title caught me on the hop, really, because her title is Making Solar Cells Work Indoors as Battery Substitutes. And I thought, first of all, why on earth would you want to do that? But now I realize there's a very, very good reason why you want to do that. So Rachel, please tell us about this work that you've been doing. Thank you.
Thank you very much, James. Hopefully my slides are showing up nice and clear. So thanks for the kind introduction. Yep, my name's Rachel Evans. I'm a professor of materials chemistry in the Department of Materials Science and Metallurgy, and I'm excited to talk to you about some of our really recent work on trying to turn solar cells into perpetual power sources so that they can work indoors as battery substitutes. So we've heard already that batteries are going to already play a critical role in solving the intermittency issue associated with renewable energy sources, including solar energy. But for some off-grid applications where we only need a low or continuous power supply, standalone solar cells might actually be the solution, provided we can design them to work indoors and to use different light sources. So one such application is to power the Internet of Things, or the IoT. And the IoT simply refers to this vast network of physical objects or things that are embedded with sensors, softwares, and other technologies, which enable them to connect to the Internet and exchange data with other devices and systems. And these objects we'll be familiar with if you think about your smart thermostat or wearable devices, but they're also applied more widely in things like industrial machinery and city infrastructure. And the IoT market is growing, and it's predicted to reach $12.6 trillion by 2030, so it's huge. And every object or thing is going to need a power supply. But the power requirements are quite small, really, from around 1 to 500 milliwatts, depending on the device. And currently, batteries are used most commonly as a power supply. But for many remote applications, the need to replace or charge these batteries is quite inconvenient. And so an alternative continuous source of energy would be really advantageous. And one possible solution then is ambient light harvesting using solar cells, which would allow for a saving of up to 1 million tons of lithium if all of the IoT batteries were replaced. The challenge is then, how do we make our solar cells work in non-standard environments, such as indoors? So how can we make solar cells work indoors? There are 3 challenges we need to overcome. The first thing is that solar cells are optimized spectrally to work under direct outdoor sunlight conditions. So this is why you typically see solar cells installed on south-facing rooftops or as fields or in fields as solar farms. The second thing then is that the spectrum of light that's given out, for example, by a white LED that we use in our homes is quite different from that to the sun. So if we compare this, here this spectrum, which represents the solar spectrum, we can see it's different to the solar spectrum or to the spectrum or output from a white LED light in shape. And the final challenge then is that indoor light, whether it comes through our windows as sunlight or it comes from an artificial light source such as an LED light, it has a really low power density and is diffuse or scattered. And solar cells typically perform really poorly under these conditions. So to make solar cells work indoors, we need to find a way of capturing diffuse low power light, spectrally converting it so that it meets the requirements of the solar cell we're going to work with, and then use it to generate electricity. And if we can do this using both natural sunlight and also artificial light sources, then we should be able to generate a continuous day and night low power energy supply. So the first challenge we have to overcome is to capture this diffuse or scattered light. And to do this, what we need to do is develop a material that can capture light over lots of angles of incidence, not just direct 90 degrees irradiation. So in other words, it needs to have a wide field of view. And what we do is we take inspiration from nature here, and particularly the compound eyes, typical of many insects, such as the horsefly shown here. And when we look at how the structure of the eyes in a bit more detail, what we see is that they are made up of hundreds to thousands of ommatidia, which are packed together in this dome-like arrangement. And each ommatidium consists of a lens at the outer surface to collect and focus the light, which is then guided onto these channels, which help trap and guide the light onto these photoreceptor cells, which detect the light and then convert it to an electrical signal. So there's been quite a lot of materials chemistry research investigating the design of different artificial compound eyes. And one such example is something known as a waveguide encoded lattice, or WELL, which was first developed by the Saravanamutu group in McMaster University, Canada. And if we look at the structure there, we can see it has these sort of channel structures, and the channels are oriented rather like the dome-like orientation of the horsefly eye. And so what the WELL consists of basically is a polymer coating into which we're then going to encode these different channels to trap and guide the light to maximize the field of view for light collection. So how do we make these things? Well, we exploit a really weird phenomenon of light that takes advantage of its tendency to refract and diffract in different circumstances. And we self-trap light beams during a photopolymerization process. So if we think of a flashlight, a standard flashlight, we know that it naturally broadens or diffracts while it passes through most transparent materials, so things like glass or air or water. But for some type of materials, for example, the same beam will trigger a transformation, such as a chemical reaction, and this causes the refractive index to change along the path with which the light beam is traveling. And this has the tendency to counteract this drive to diverge, and instead it results in this sort of focusing effect. And so we get the formation of these channels within our photopolymer sample. So in the lab, this is how we make these things quite simply. We take a white LED light and we shine it through a few lenses and then pass it through a mask, and that's going to give us our pattern that we're going to encode into our polymer film. And then it shines onto our precursor solution. And so when the light hits this precursor solution here shown in orange, this triggers this chemical reaction, this photopolymerization, and the material transforms from a liquid to a solid material. Any part of the sample that's directly hit by the mask will polymerize first, and this is where the channels will form. And then by controlling the pattern of the mask and the orientation of the lenses, we can control the orientation of the waveguide channels that we embed within our material. So here in this case, we see a simple checkerboard pattern embedded into this polymeric film. So we have a way of capturing and transporting diffuse light. And the next challenge then is to tune the spectrum of the incident light source so that it better matches the region where the solar cell that we're going to integrate it with performs most efficiently. And what we're going to do is we're going to add a fluorophore into the well. And so a fluorophore is simply a light-emitting molecule that absorbs light and then re-emits it. It absorbs light of one color and then re-emits it at a different color or wavelength, losing a little bit of energy for heat. And when we choose a fluorophore for this application, what we need to do is find one that absorbs strongly where our light source, our LED in this case, gives out light, and then emits strongly where the solar cell has its best efficiency. So if we look at these two graphs here, we can see in the absorption graph, the gray area is the output from our LED. And then in the emission graph, the gray area corresponds to where our solar cell performs best. And all of the other colored lines are basically the absorption and the emission from different fluorophores or light emitting molecules. And hopefully we can see that the orange line in this case gives the best compromise and the best option, the best of both worlds. So we get the maximum absorption and the maximum emission where we need our material to work. So the next step is to integrate the fluorophore with the well to make a luminescent waveguide encoded lattice or L-well. And we just do this by adding the fluorophore to the photopolymer solution before we encode the waveguide. And so you can see our bulk well here under UV light, and it gives out this green fluorescence. And when we zoom in, we can see, in fact, that there are these encoded waveguides within the polymer film. So how does this lead then to an enhanced field of light for collection? So what we do is we compare the L-well templated film with a bulk polymer film with no channels in it whatsoever. And we shine light on the top surface at different angles of incidence. And then we measure the light that's collected below the sample. And what we see is when we have the waveguides, we're able to collect light at lots of different angles of incidence from -35 to 35 degrees. But when there are no light guides present, we only manage to collect light when it's directly incident on the top surface at 0 degrees. So then finally, the next step is to integrate our wells and test them with a solar cell and see how it affects the performance. And so what we do is we just, in these proof of concept experiments, we place the well or either the well or an on-pattern film on top of the solar cell, and then we measure the cell performance under different incident light conditions. So the first one is direct sunlight at 0 degrees. The second is indirect sunlight at an angle of 20 degrees. Then we use diffuse direct sunlight, and then finally an indoor LED. And hopefully you can see that these all have quite different incident powers. And excitingly, in all cases, when we add our well, performance greatly is greatly enhanced compared to a bulk polymer film due to the presence of these waveguides, which improve the collection of both diffuse light over and direct light over multiple angles of incidence. So just to summarize then, I hope I've convinced you that L-wells offer a unique approach to enhancing solar cell performance in non-standard conditions. And importantly, this complements the development of new solar cell materials, since they can be tuned and retrofitted to work with any solar cell. The wells enhance the angular collection efficiency of light relative to a bulk polymer film, and this is really critical for improving performance under diffuse indoor light conditions. So there's always stuff to be done, and the remaining challenge that really requires further optimization is this spectral conversion bit that will allow us to work under both sunlight and with artificial light. So we have this day to night power source, and this is really dependent on the fluorophore concentration, the film thickness, and a lot of work is being undertaken right now to try and tune and optimize the system so that we can really have day to night power using a photovoltaic cell indoors. And so just finally, I'd like to thank my group, particularly Helen Kunsel-Garcia and Takashi Lawson, who performed the work, and our collaborators on the project, Kalai Saravanamatu and Marina Freitag in Newcastle, the various funding agencies. And you can find out more about our work on lots of different photoactive materials at our website, www.labevans.co.uk. Thank you very much for listening.
Thanks very much, Rachel. Will you come and coat my solar cells on my roof for me soon? Because the sunlight has been very diffuse of late.
Yes.
It's very good. Thank you very much indeed. So we've got a range of questions coming in, and I'm going to try and sort of merge them into sort of super questions so we can cover several topics at once. So first of all, there's a group of questions which are aimed at you, Alex, so get ready. And I suppose they're along the lines that people find it slightly perplexing that the disordered material is better for the storage. And wonder whether you really had any ideas about why that was. I mean, as an explanation.
Yeah, and the first thing to say is it came as a surprise to us. I didn't have time to go into it, but it wasn't our initial hypothesis, but it was something that came out of the data. In terms of why it happens, we're actively looking into it now. We don't have all the answers there, but we've got a few different theories we're looking at. But one is that when you've got these more disordered materials, or where you have smaller sheets of the graphene material, you have more edges and defects in the structure. So the imperfections in the material might actually be where you can store energy, store charge more efficiently. And we're looking at testing that in a few different ways now.
And if you use this phrase amorphous carbon, is that something else from this material you're using, or is that an imprecise term? Yeah, so the word amorphous here, it means, I guess, something lacking a repeating structure or lacking a crystalline structure. And so, yeah, our goal is very much to make these carbons now as almost as amorphous or as messy as possible. And we've got ways to do that in the lab, where we can control the synthesis, and the preliminary results look promising. We can make them more amorphous, and then they do store more energy. Okay. And so we're working on that actively. So moving around, Siân, if I could direct a couple of things at you. So it's really thinking about batteries, about whether or not lithium batteries have reached some kind of theoretical limit. And if you had to look into your crystal ball, what would you see as the kinds of batteries being used on a big scale for this energy balancing? What would you?
Okay, all right. So first of all, lithium-ion batteries have not reached their theoretical limit, but there's been a lot of improvement since the first cells were commercialized, and the capacity and the voltages have increased significantly, as have the lifetimes. What I'd say is a lot of work has already been done, so finding and identifying improvements is perhaps harder. but I'd say we're not there yet. And then the second question about what the answer will be in terms of storage, I think the answer will be a whole bunch of different things. And that it won't just be one thing, it will be a mix of different storage devices, both to enable different rates, so you can charge and discharge at different rates, but also just for different timescales. So storing at short timescales will be very different to storing in long timescales. And it won't just be batteries, it will be mechanical storage, things like compressed air, pumping water up a hill, particularly for long timescales, are really much more efficient than anything sort of battery related.
And the sort of the supplementary question to that, which I suppose is in the back of everybody's mind, is this issue about recycling the batteries. I understand they're very complex structures. So are people working on how one would go about recycling a lithium battery or something, or are we in danger of generating a pile of broken lithium batteries?
I mean, so there's a huge amount of work looking at recycling batteries. I mean, they're complicated. I mean, the diagram made it look very simple, but they're very complicated structures. And so extracting the useful components is something which takes a lot of thought, and there are lots of clever ideas about how one can do that, to either by taking, say, a battery from the car and using that in a second life. So say taking your car battery, using that for grid storage, where perhaps you're less concerned if the capacity isn't exactly what it was when it was first made, or alternatively stripping the components out, processing them in some way, so then you can reuse them either for another battery or for something else. So yeah, there's a huge amount of work on that.
Okay, thank you. So Rachel, if I can turn to you now. So there's questions about the fluorophores and the light capturing devices. I suppose the question is really, do you imagine these being used on a very large scale, the field of PVs, or do you imagine that the principal application of these kinds of adaptations are going to be in the diffuse situation?
So primarily in this example that we've talked about today, in the microstructured well systems, we're looking at really small solar cells. So imagine the type of solar cells that you might use to power your calculator, really small scale systems. But we're actually working on a kind of related technology in order to use a similar approach, but without the templating, but using this spectral shifting with the fluorophores to make solar cells work in the built environment. So things like for building integrated photovoltaics. So you wouldn't imagine them to be used in a solar farm, for example, but you might imagine them being integrated as part of functional architecture. You might have seen that the materials were really colored, so you can build them into the building design to power things like the signs on bus stops displays, or charging points on a park bench or something like that. So the advantage is because they can absorb this diffuse light, you don't have to have direct sunlight on them, so you can try and make your solar cells work in places where they normally wouldn't be bothered. We normally wouldn't install them because they wouldn't be very good.
And I mean, it's slightly, you've kind of answered it, but in terms of efficiency, if you compare these kinds of solar cells that you're talking about with the conventional ones, what is how much have you lost, as it were?
So you cannot compare like for like, because obviously if you take a solar cell and you put it directly under sunlight, it's going to perform much better than if that efficiency will be much higher than if you put a layer on top of it, and you'll reduce the efficiency. The idea is to try and make solar cells work in places where you wouldn't normally use them, because they can't use the type of light that's available. And so the absolute efficiency values don't make, we use quite different metrics compared to the solar cell community, for example, because we're looking at the light trapping processes, the light conversion processes, more than the direct current output, as it were, from the device. So it's to make them more versatile.
So can we switch back to you for a minute, Alex? There's a question about the supercapacitors, and obviously triggered by the picture of the bus, I suppose. Is it possible that this kind of technology could be used to run trains and so on? I mean, I've seen it running trams where they charge up when they get to a bus stop. And is it conceivable that you could take it further?
I think it's been demonstrated for intercity trains. So when you're doing sort of short distances between stops, they have enough power in the supercapacitors to get you from one station to the next. I think if you look at longer distance sort of rail travel, then it's not feasible with the current capacity that the devices have. And they're perfect for these sort of intercity things where you have a lot of stopping and starting, recovering energy in the supercapacitors, but also powering the devices with the supercapacitors.
Are we talking about, 200 or 300 meters to the next charge up, or a mile or two? Do you have a sense about where it sits?
I would say something like sub 1 mile between stops would be my guess.
Yeah. Okay, that's fine. Thank you. You didn't mention this, Siân, but I'm going to throw this one at you about these flow batteries for energy storage. Do you just want to tell people what they are?
I'm actually going to refer this to Alex because he has a flow battery project.
I refer the question to the honourable member for chemistry.
Yeah, I can comment briefly on it.
Just tell people what flow batteries are first of all before you.
So in a flow battery, you've got 2 huge tanks of liquid, and in those big tanks of liquid are molecules that you can charge up, basically. And so you flow those molecules from the tank over a small battery, and then they go back into the tank where they're stored when they're charged up. And so later on, when you need that energy back, you can run your flow battery the other way and get your energy. What's nice about them is you can make them really big quite easily, because you just make your tank bigger and then you can store more energy. So from an engineering perspective, they're quite nice. And you might have seen sort of news in China, they've got a 100 megawatt redox flow battery. So a large power station would be, it's not far off a large power station, basically. It's a huge battery that they've got in Dalian in China. So I think that's one of the sort of the next generation grid technologies that we'll see coming alongside the more familiar batteries that we know about.
Okay, that's very good. Thank you. So I'm not going to let you off the hook, Siân. I'm going to ask another question. And this is again going back to the issue of energy storage on the grid. And the question was asked whether, rather than just having one very big installations, is there some sense in having a highly distributed system where everyone has a little bit of storage, rather than concentrating in very large places? Does that make any sense?
So I should preface my answer with I'm not an engineer, and so that's something really sort of an engineering problem. But I do think that having sort of more localized grids and sort of having storage closer to where the demand is useful. But it's then how do you do that within a grid that exists?
Thank you. And I think we're sort of drawing to a close here now, but perhaps Rachel, you could address a sort of a rather global question, and that is, could you characterize what is particularly unique about the Cambridge way of thinking about these problems, or is there something that the university here brings to this which sets us apart? Because obviously it's an area where a huge number of people are working.
Yeah, absolutely. I mean, I think there's quite a collaborative environment here at the university. So obviously we've got three different people here. Actually, we're all essentially chemists working in very different departments, and so you can see that there are lots of synergies in the research going on at the university, which helps, I think, stimulate new ideas and concepts. So there are lots of we have lots of research centres. So there's the energy at Cambridge Research Centre, which focuses on, in this case, sort of solutions to energy storage and energy generation, so on. So I think it's really that collaborative environment and that interdisciplinary approach that will really lend itself to thinking out of the box and coming out with really creative solutions to these problems.
And I would echo that completely if I can put in my oar here. It's my colleagues say that no matter what the problem is you're working on, there's always someone else in Cambridge that will help you with that, that will have some input, will have some special knowledge, and that's what makes this, the whole environment around here so productive. So I think I'm going to draw this to a close now. So thank you very much to Rachel, Alex, and Siân for talking to us this evening and giving us a flavour of what they do and answering our questions so skillfully. Thank you for the team that you can't see that have put all this together in the background. And I want to remind you that the second in these series of webinars will be on the 27th of November and will be on the subject of AI and how it is accelerating research here in Cambridge. And you should be able to find the details about how you can log into this from the alumni website. So thank you very much for joining us this evening. I hope you have a pleasant evening. Goodbye.